In Chapter 17, we're going to continue our study of the atmosphere, this time taking a look at moisture, specifically water vapor in the atmosphere, and how that leads to the formation of clouds and precipitation. So we know that water vapor, which is the gas state of water, exists in the atmosphere along with the other gases, oxygen, nitrogen, and carbon dioxide. It mixes freely with those in the atmosphere. But what's unique about water is that it's the only substance that we find on Earth that naturally exists in all three states of matter. Solid in the form of ice, liquid, of course, in the form of water, and then gas in the form of steam, or what we'll refer to it in this chapter, water vapor. What makes these states of matter different is the amount of heat contained within them, and then the arrangement of the water molecules. So ice is composed of water molecules that are very tightly packed towards one another. They are not free to move. They can only kind of vibrate in place. When heat is added, if you have an ice cube and you add heat to it, in other words, you take it out of the freezer and you set it out on your counter, you're essentially adding heat to it. And as that happens, the solid piece of ice starts to melt. What happens is that as the heat is added, those molecules start to speed up. And as they speed up, they can start to spread further apart. When they increase their speed enough, they break the attractions between the individual water molecules, and this results in melting. If we continue to add heat, some of the molecules there will acquire enough energy to break completely free and escape up into the air. And so gases have a lot more molecular motion, a lot more molecular energy than the liquid form, and then the liquid form has a lot more than the solid form. So we're going to watch a smart figure video now that goes into a little bit more detail about these phase changes and how we can add heat or release heat in order to get to these three different states of matter of water.
Figure. After watching this video, you should be able to describe how water can change its state and what the names are for the different processes that describe the different states of change. So let's start with a common phenomenon that happens on my deck every summer. When I pour myself a glass of iced tea and go out and sit on the deck, I notice that the exterior of my iced tea glass starts to develop all these little droplets of water all over it. What's going on here? Well, it has to do with changes in the state of water. So water exists in three states: solid, liquid, and gas. The solid form of water, of course, is called ice. The liquid form we just call water. And then the gaseous form of water is called water vapor. Water can transform from vapor to liquid, or from liquid to solid, or even from solid to vapor. So let's take a look at some of these processes. Let's first consider melting. So this is what happens when ice melts and becomes liquid water. For a single gram of water, it takes about 80 calories of heat to make that transition happen. The reverse transition, which is of course freezing, takes the same amount of energy. So 80 calories of heat are released when water freezes. That might be a little bit counterintuitive to think of water releasing heat when it freezes, but that's exactly what happens. All right, let's consider a third possibility here, and that is sublimation. This is where ice, solid water, goes directly to the gaseous form, and it doesn't go through the liquid phase in between. Well, it takes about 680 calories of heat to be added to the ice in order to get it to sublimate. The opposite is when the gas turns directly into a solid, and that's called deposition. And deposition releases 680 calories of heat. So you can see here that in part of our picture so far, we've been looking at transitions that take 80 calories of heat or release 80 calories of heat. With sublimation and deposition, we've got 680 calories of heat. I bet you can make a prediction here about what's going to happen when we transform liquid water into gas, when we evaporate liquid water. You guessed it, 680 minus 80 gives you 600 calories of heat. So in order to get 1 gram of water to turn into 1 gram of water vapor, you've got to add 600 calories of heat. The opposite phase transition when water vapor turns to liquid is called condensation. And again, that will release that same amount of heat, 600 calories of heat. Condensation is, of course, what's going on with my glass of iced tea. So those little droplets of water on the outside are coming from water that's in the air. You can't see it, it's water vapor, but when it hits that cold surface there, it has a substance to which it can impart that load of heat. So basically the water then releases that heat and it goes from the vapor phase into the liquid phase, coalescing as droplets on my glass. That's a lovely example of condensation. Okay, let me give you two other options. You tell me what's going on. Here's the first one. This is frost, such as might develop on a window pane or might develop on your car windshield after a cold night. So which of the different phase changes is this representative of? Okay, so you're ending up with ice, so it's got to be one of the two blue arrows that go to ice. Basically, this is happening with water vapor in the air, so you're not having a liquid phase. So it's an example of deposition, all right, where we're going directly from water vapor down to solid ice. Very good. Let's check the last one here. There's not much to see here, but this is a foggy coast. Maybe the coast of like Maine or California or someplace like that. You can see there's a lighthouse. This fog is basically a cloud that's sitting on the ground. So which of the phase changes is at work to produce this scene? Well, it's actually just like the glass of iced tea. It's condensation, where you've got vapor that's turning into little droplets of liquid. Those little droplets of liquid make up the fog. They're suspended in the air, so rather than coalescing around an iced tea glass, they're coalescing around little tiny airborne nuclei, little particles of dust and stuff like that. And of course, if the droplets get too large, then they'll fall out of the air, and that'll be an example of precipitation. Okay, so hopefully you got a better sense of the way that water can transform from one phase to another.
So as you saw from the smart figure video, we can see different examples of these different phase changes if we just look in the world around us. So how do we measure water vapor in the air? Well, that's humidity. Okay, so the term humidity just refers to the amount of water vapor in the air. But there are different methods that we can use to express this amount. So the first one we have is saturation. So saturation means that we get to a point where the air is filled with so much water vapor, it's full. It can't hold anymore. Okay, so think about this as an example. Okay, so you have a jar and you've got some water in it, and of course air. Can't see that air, but we know it's in there, and you close up this jar. The water will evaporate, and so those water molecules are going to leave the liquid water and go up into the air as water vapor. As that happens, we get a pressure that starts to build up in the air. This is because the water molecules as water vapor move faster than those in the liquid. Remember, they have more energy. So if they have more energy, then they're going to start to exert some pressure on the water below. This pressure is called vapor pressure. Okay. As more and more water molecules start to escape from the water surface, the vapor pressure continues to increase. This forces more and more of the water vapor molecules to return to liquid. So we get this situation where we have water that's evaporating, so liquid water becoming water vapor. And this sets up this vapor pressure, okay? Well, this vapor pressure then is going to increase as more and more water molecules become or convert into water vapor, but then it starts to press them back into a liquid. So you get this cycle. because at some point you achieve saturation. The fact that the atmosphere, the air, can't hold any more water. So some of that water is going to have to settle back out. That water vapor is going to have to be converted back to liquid water. Saturation is dependent upon temperature. Okay. So if we have warm air, it has a higher capacity. It can hold more water vapor. Lower temperatures can't. There is a table in your book on page 520, table 17.1, that gives you the amount of water vapor that's needed to saturate 1 kilogram of dry air at various temperatures. So if we look at 25 degrees Celsius, 77 degrees Fahrenheit, it takes 20 grams of water vapor for it to be saturated, for the air to be saturated. But if we increase that temperature to 40 degrees Celsius or 104 degrees Fahrenheit, then it takes 47 grams. Okay. And once we reach that point, once we reach the point of saturation, then the air can't hold any more moisture, can't hold any more water vapor. So in looking at how we measure humidity, we can do this through the mixing ratio. We can do it through the concept of relative humidity, which is probably what most people are familiar with. Or we can look at the dew point temperature. So the mixing ratio is the mass of water vapor in a unit of air compared to the remaining mass of dry air. So we've got a ratio. We're comparing the mass of water vapor to the mass of dry air. This is not affected by changes in pressure or temperature, but it is time consuming. We have to actually directly sample this air. So it's difficult to do and it's time consuming to do. The relative humidity is also a ratio, but it's the ratio of the water vapor content compared with the amount of water vapor required for saturation. So this is affected, as we've learned, by changing the moisture or changing the temperature. And so I just provided you that example that, we go from 25 degrees Celsius to 40 degrees Celsius. It takes a lot more water vapor content to reach saturation. So what we do with the relative humidity, let's say there's 20 grams of water vapor in the air, okay? If there's 20 grams, then at 77 degrees Fahrenheit or 25 degrees Celsius, we're at 100% relative humidity because it only takes 20 grams to reach saturation. But if we have 20 grams of water vapor content and it's 35 degrees Celsius outside or 95 degrees Fahrenheit, which takes 35, then we are little more than 50% humidity. Okay, so relative humidity is when we relate the water vapor content with the saturation point. This is an easy measurement, and this is often how humidity is stated if you're watching the weather and you say, how humid is it outside today? And they say, well, it's 95%. And really what that means is that the air is currently holding 95% of the water vapor that it can hold. And so we call that, a really humid day, like pretty much every day in the summer around here. And that's because that's how much water vapor is in the air. Now, in your book on page 521, there's kind of a little demonstration here of measuring what's happening as we get water vapor, as we kind of become saturated. So you've got initial or figure A, your initial conditions. The temperature is 25 degrees Celsius. We've got 5 grams of water vapor plus, in 1 kilogram dry air. So the relative humidity is 25%. Because there's 5 grams, it takes 20 to reach saturation. So we're at 25%. Now, as that vapor starts to evaporate, now we have, or as the water starts to evaporate, now we have more water vapor. So now we have 10 grams of water vapor. So we're at 50% humidity. And if that evaporation continues and we get to 20 grams of water vapor, now we're at 100% relative humidity. Okay. Can we get beyond 100%? No, because that vapor pressure would start to cause the water vapor to turn back into liquid water. So it would cause condensation. When the water vapor content remains constant, a decrease in temperature results in an increase in relative humidity. And this is shown for you at the top of page 522, figure 17.5. In this one, we've still got 25 degrees Celsius. We start out, we've got 10 grams of water vapor, so we're at 50% relative humidity. Okay, because it takes 20 grams to achieve saturation. If we decrease the temperature to 15 degrees Celsius, now we're at 100% humidity because it only takes 10 grams to be saturated at 15 degrees. Okay. Now, if we drop the temperature more to 5 degrees, well, the air is going to be saturated at 5 grams per kilogram of air. 5 grams of water vapor are going to condense to form liquid water because we can't get over 100% relative humidity. So the vapor pressure becomes so great that it causes the condensation of 5 grams of that water vapor back into liquid water. This is what happens in the atmosphere. When rising air reaches an elevation where it's cooled below its dew point temperature, which we'll talk about in a second, some of that water vapor condenses, and that's what forms clouds. And once clouds have formed, that moisture is no longer a part of the measure of the water vapor content of the air. Okay. So that's relative humidity. That as we increase temperature, it takes more water vapor in the air to be saturated. Now, the last way that we can measure humidity is with dew point. So dew point temperature, or the dew point, is the temperature at which the condensation is going to occur. So the temperature at which water vapor begins to condense. So we're going to watch a smart figure video based on figure 17.8 at the top of page 523, which shows us a dew point map, and we're going to talk about the results of achieving that dew point temperature.
Hello, this is Callan Bentley. Welcome back for another smart figure. After watching this video, you should be able to describe what the dew point temperature is and why it results in the formation of dew. A household example of dew can be seen in this image. Here's a nice cold glass of iced tea that has condensation all over the outside. So what's happening here is little water molecules that are in the air surrounding this glass are perfectly stable out there in the air. They're happy to be in the vapor phase unless their temperature gets lowered. And when they up against this glass, they encounter much cooler temperatures. And that causes them basically to give up some heat and exit the vapor phase and condense, so they become part of the liquid phase, and they coalesce in these little droplets on the exterior of the glass. You may have seen the same thing in your yard on a cold morning. When you walk outside, you'll notice that there are dewdrops on the grass, or perhaps covering your windshield of your car. What's going on here? Well, it basically has to do with how saturated with water the air is. So here's an experiment. We've got a flask, and in this flask are 7 grams of water vapor. That's our sort of starting point. And this is at 20 degrees Celsius. And what we're going to do is, over the course of the experiment, we're going to cool it down, going towards the right. Once we get it down to 10 degrees Celsius, you can see that the air has become saturated. Okay, so basically its relative humidity is 100%. In the first example, basically we've got 7 grams of water vapor content, but the saturation mixing ratio, which you can get from table 12.1 in your textbook, that was 14 grams. So 7 divided by 14 was 50%. So that air was only 50% saturated relative to water. But by the time we get it down to 10 degrees Celsius, we have a new mixing ratio, and that's 7 grams. So 7 divided by 7 gives you 100%. So that's the relative humidity there. If it gets any cooler than that, some of that water vapor is going to have to condense out of the air. And that, of course, is what we want to do next. So now we're going to drop it down to 0 degrees Celsius. And at 0 degrees, the saturation mixing ratio is 3.5 grams. And so what's going to end up happening here is that that's all the water vapor that air can hold. And so it's going to remain at 3.5 grams, which is 100%. But 3.5 grams of water vapor in the air when you had 7 to start off with means that 7 is going to have to leave the vapor phase and enter the liquid phase. It's going to condense, and so you end up getting 3.5 grams of water at the bottom of the flask. This is a map which shows dew point temperature. So basically, this map considers how saturated the air is, how much water is already actually in the air. And so, therefore, how much would you have to cool that package of air in order to get it to condense? And you can see in more humid areas of the country that you don't have to cool the air nearly as much in order to get it to condense out of the air. So here in the southeast, for instance, you've got dew point temperatures that are around 70 degrees. That's really, really different from, say, Nevada and Utah. Over here in the American Southwest, you can see the dew point temperature there is all the way down at 20 degrees. So you basically have to drop that temperature of that air a lot further, an additional 50 degrees, in order to trigger condensation from that air. So why is that? Why is the dew point temperature so much lower in Utah than it is, say, in Tennessee? Hopefully you deduce that it's all about humidity. Utah has relatively arid air, and so you've got to cool it a lot more before you can get its water vapor to condense out. In general, Tennessee has much more humid air, and so basically you don't have to cool it nearly as much because it's already so much closer to saturation.
So there you saw dew point, and you've probably seen that on the news. Just another way to measure the humidity in the air. So we have some instruments, some tools that we use called hygrometers that can measure the content of the air. And the easiest ones to use are psychrometers. A psychrometer, I'll show you, here's a picture of a psychrometer. So basically you've got 2 thermometers that are hung side by side. One is called the dry bulb, and that's what's going to measure the air temperature. And then the other is called the wet bulb. It has a piece of cloth on the end of it, and it's going to be saturated with water, and then it's going to be spun around. So there's going to be a little handle there, and it's going to be spun around. And what's going to happen is that the water is going to evaporate from that piece of cloth, absorbing heat energy. And as it does that, the temperature starts to drop. Okay. The amount of cooling that takes place is proportional to the dryness of the air. So if the air is really dry, then the cloth wick then is going to evaporate more. The larger the difference between the wet bulb and the dry bulb, the larger or the lower the relative humidity. So if you have, 90 degrees outside and that's your dry bulb thermometer, and then on your wet bulb thermometer, you have 20 degrees, then that would mean that your relative humidity is fairly low. In the back of your book, there is a table that allows you to determine the relative humidity and the dew point temperature from the temperatures that you get from a psychrometer. And when we come back in the lab, we're going to use a sling psychrometer in order to measure relative humidity and dew point. Now, with meteorologists, they have various types of electric hygrometers, which are a little bit more scientific and a little bit more exact than using this sling psychrometer. So we're going to switch gears a little bit now and talk about some temperature changes that can occur. So if we think back to those smart figure videos you've watched and seeing that cup of iced tea that has condensation on the outside of it, we know that condensation occurs when the air is cooled to that dew point temperature. So the air is flying all around, it hits that glass that's cold, it cools down, and then it's able to go from the water vapor, the gaseous form, back to water, the liquid form. So condensation then can produce dew, okay? It can produce fog, or it can produce clouds. So heat, we talked about in the last chapter, we talked about how, the sun's rays come in through the clouds. About 50% or so reaches the Earth's surface. That heat is readily exchanged between the ground and the air directly above it. As the ground loses heat in the evening, dew may condense on the grass, on the ground, and then fog could form slightly above Earth's surface. So surface cooling, so we're talking about the surface of the Earth, so surface cooling that occurs after sunset produces condensation, can produce dew, can produce fog. Cloud formation, though, happens typically during the warmest part of the day. So there has to be some other mechanism at play to allow that water vapor to condensate to form clouds. Okay, so surface cooling leads us to dew and fog formation, but adiabatic temperature changes lead us to cloud formation. Okay. So gas molecules, as we learned, move all around. Okay, so gas molecules have the highest amount of energy of the three states of matter, and so they're in constant motion. They're moving around, so they contain a lot of energy. Gases that absorb heat energy move faster, and gases that release heat energy move slower. Okay. Temperature changes that occur without heat being added are called adiabatic temperature changes. And this has to do with pressure. Okay, so let me kind of go through that again. So if we have a gas, okay, those molecules are in constant motion. If we add heat, they speed up faster. Okay, if we take away heat, they slow down and eventually may condensate. Okay, so it's easy to see what happens when we add heat. But in adiabatic temperature changes, there is no heat energy being added or subtracted. It all has to do with the change in air pressure. Okay. This is due to a particular gas law called Gay-Lussac's law. Gay-Lussac was an individual who studied gases, and he came up with the idea that temperature and pressure are related. Okay. If we increase pressure, we increase temperature. If we decrease pressure, we decrease temperature, okay? So adiabatic temperature changes are based on the idea of Gay-Lussac's law, that if air is compressed, okay, so we're increasing pressure, then it gets warmer because we're increasing temperature. And when air is allowed to expand, in other words, we've lowered the pressure, then it cools down. So adiabatic temperature changes relate specifically to changes in temperature due to pressure, okay? If the gas is compressed, in other words, the air is compressed because pressure increases, then the air also gets warmer. If the air expands, its pressure is lowered, then the temperature also becomes cooler. So there are three kind of different things that we can look at when it comes to adiabatic cooling. So the first thing is kind of trying to understand how we measure this. And so we have what's called a parcel. So this is the first term that you need to know, that we have this imaginary column of air, okay? It's about a few hundred cubic meters in volume, and it acts independently of the air around it. So we just imagine this column of air, okay? No heat is going to be transferred in or out, because remember, we're not looking at heat energy. We're just looking at what happens with pressure, okay? So we've got this column of air. That's called our parcel, okay? So then we look at what happens as that parcel moves. That's all I have. Okay. So here is the figure. This is on page 525 in your book, and this shows us dry versus wet adiabatic rates of cooling. So we've got our parcel of air, okay? So here's our little parcel of air right here in the middle. So let's compare dry adiabatic rate versus the wet adiabatic rate. So atmospheric pressure decreases with height. Remember, we talked about that in the last chapter, that as we go higher and higher, the atmospheric pressure drops. And that's why, you know, it's harder to take in breaths as you get higher and higher and higher. Anytime a parcel of air moves upward, the pressure surrounding it decreases. So remember, if pressure decreases, then that gas is going to expand, and therefore it's going to cool, okay? Unsaturated air, because we're talking about dry adiabatic cooling, unsaturated air cools at a constant rate of 10 degrees Celsius for every 1,000 meters as it ascends into the atmosphere. So here is our parcel of air, okay? So at the surface, we're at 32 degrees Celsius, okay? We go up 1,000 meters, air drops by 10 degrees Celsius, or the temperature drops by 10 degrees Celsius, okay? We go up another 1,000 meters. It drops by another 10 degrees Celsius because it's continuing to expand. Notice how this little air bubble is bigger than this one. We go up another 3,000 or another 1,000 meters to 3,000 meters. Now we're at 2 degrees Celsius and our gas has continued to expand. So what's happening? Pressure's dropping, so temperature is dropping, okay? And then the same thing happens as it descends. For every 1,000 meters it descends closer to the surface, the air is heated by 10 degrees. Okay, so this is called dry adiabatic rate, okay? Because the air, we're not talking about any form of saturation here, okay? Dry air. Now, if the column of air gets high enough, it will eventually cool down to its dew point, which triggers condensation. The altitude at which that happens is called the lifting condensation level or condensation level. So in this example, it's right around 3,000 meters, okay? So below that, this has been due to the dry adiabatic rate, okay? But once we get above that, now we're going to get into the wet adiabatic cooling, okay? At this level, the latent heat that was absorbed by the water vapor when it was evaporating is released as sensible heat. Okay, so remember back to that very first smart figure video that we saw that, you know, those water molecules take in and release energy, typically in the form of heat. Okay, so when the liquid water became water vapor, it took heat to make that happen. Okay, and that was referred to as latent heat. Okay, now it's going to be actually released as the water vapor starts to condensate in clouds. It's released as what we call sensible heat. So what happens is that as the air continues to move higher in the atmosphere, it's still going to get cooler, but that sensible heat that's being released is going to slow down the rate at which it's cooling. Okay. And so you see here we have about 2 degrees at our condensation level. We go up another 1,000 meters, we've only dropped 5 degrees Celsius, okay, instead of 10. We go up another 1,000 meters, we've dropped another 5 degrees Celsius. So this is referred to as the wet adiabatic rate of cooling because we're looking at what's happening above the condensation level. The amount of latent heat that's going to be released depends on how much moisture is in this air. So the wet adiabatic rate varies from about 5 degrees Celsius, like we're seeing here in air that's really saturated, to about 9 degrees Celsius. So it's just a degree less than this for air that's pretty low. So as air rises, it gets cooler because it starts to expand. Once it reaches the condensation level and still rises, it's still going to get cooler, but the rate at which it gets cooler slows down. Okay. So that is how we get cloud formation even when it's cold. Okay, because we're getting above this condensation level. So why does air rise? Sometimes, and sometimes it doesn't. So here, this air is rising, it does produce clouds. We get to the condensation level, it gets up high enough, it does produce clouds. So what are some processes that do that? Well, air tries to resist vertical movement. Air near the surface tends to stay there. Air aloft or up higher in the atmosphere tends to stay there. But there are 4 processes that we can look at that cause air to rise: orographic lifting, frontal lifting, convergence, and localized convective lifting. So we're going to look at orographic lifting first, and then we're going to watch a smart figure video on the other types. So here is the image from your book on page 526 due to orographic lifting. Remember, oro refers to mountains. So with orographic lifting, this is when a mountain range acts as like a barrier to the flow of air. So we've got wind coming off the ocean here, okay, going over this little smaller mountain range here. And as it gets up to this Sierra Nevada range, the taller mountain range, adiabatic cooling generates clouds and a lot of precipitation because that water vapor is going to condense and then fall back to Earth as precipitation. But By the time the air gets over that mountain range, called the leeward slope, it's lost its moisture. So we don't get clouds. The air is going to descend. We don't get clouds. We don't get precipitation because we get adiabatic warming as that air falls back down. So the leeward side is in what we refer to as a rain shadow and can be a desert like the Great Basin that we've talked about before. It's only a few hundred miles from the ocean, but it's cut off from that moisture by the Sierra Nevada mountain range. And we see this in Mongolia with the Gobi Desert. We see the Patagonia Desert in Argentina. And it's because as the air lifts up out of the lifts up over the mountains, we get condensation and then lots of precipitation. And as it gets across the mountains and starts to come back down, it's warming up. And therefore, we lose the clouds, we lose the condensation, and therefore the precipitation. So now we'll watch the smart figure video.
Hi there, this is Callan Bentley. Welcome back for another smart figure. After watching this video, you should be able to describe how convergence results in frontal wedging and cloud formation. Let's begin by taking a look at localized convective lifting. This is what happens when, say, you've got one area of the ground like this patch of farmland here that's darker than the surrounding areas. It ends up absorbing more of the sun's energy, and as a result, it warms up the air that's immediately above it. That warm air then wants to rise because it's less dense than the surrounding cooler air. That generates this package of air that rises up, and that's called a thermal. Eagles and vultures really like to find thermals, and they coast around on them as a way of saving energy. Eventually that thermal will cross the condensation level. Basically that's the level where the temperature is low enough that the water vapor is no longer stable in the air and it starts to condense out of the air and glom onto little dust particles and things like that, and that makes clouds. Okay, so that's the basic situation. Now consider this image. This is a satellite image looking down at the coast of Florida. So the coast of Florida basically would be outlined something like that, and you can see that there are clouds over the land but not over the sea, or not nearly as much over the sea. So what's going on here? Okay, the land, we know, tends to get warmer faster, and it tends to get to a higher temperature than the ocean does. The water has a really high heat capacity. It can absorb lots and lots of heat before its temperature changes very much. So the land is warming up, the air over the land is rising, and that generates these packages of air that are crossing that condensation level and forming clouds. Now, when that air is all rising away from the land, what does that do to the air pressure there on the land? Well, it reduces it, and that's going to cause air to move in from the surrounding ocean to take its place. So you end up getting this air pattern that is shown here by the green arrows, cold air moving sideways off the ocean over the land, getting warmed up, and then rising. And then that rising air, of course, generates the clouds. So this is the sketch in your textbook that sort of demonstrates that basic idea. This is called convergence. Now this is the part of the textbook that we really wanted to get to here. We have two air masses that are colliding. One is a warm air mass and the other one is a cold air mass. The cold air mass is moving in from the right. The warm air mass is moving in from the left. As the two meet, because the warm air is less dense than the cold air, the warm air ends up getting shoved up into the air. And of course, then it's going to cross that condensation level, and that's going to trigger the formation of clouds. And then those clouds are going to likely drop their load of moisture as rain. So this is where these massive thunderstorms frequently come from when you end up getting a cold front moving into your area, because that warm air is essentially getting shoved upwards by this wedge of cold air that shoves its way underneath. Now imagine a similar situation where we took away the cold air and instead replaced it with something like a mountain range or something like that. What sort of situation would you get there? Well, whether it's a mass of cold air or whether it's the Sierra Nevada mountains, we end up seeing basically the same thing happening. So air masses are forced up and over that obstacle, and they can cross the condensation level as they go up and over, and that ends up resulting in this case, the rain shadow effect. So all the clouds basically get pulled out by the mountains. They end up dropping their precipitation load on the mountains, and then there's very little moisture left by the time that those air masses get over towards the Great Basin Desert.
So now we've looked at what makes clouds, okay? So why are clouds different sizes? Why do sometimes we have clouds without precipitation and sometimes we have clouds that dump a lot of precipitation on us? Well, it has to do with how stable the air is. And we're going to watch another smart figure video that walks us through absolute stability, absolute instability, and conditional instability, which are demonstrated for you on pages 529 and 530.
Hello there, this is Callan Bentley. Welcome back for another Smart Figure. In this video, we're going to take a look at atmospheric stability. And by the end of the video, you will have a better sense of what conditions cause the atmosphere to be stable or unstable. Okay, let's first consider this situation here. Look over at the left side of this picture and you'll notice that it's showing the environmental lapse rate there. In other words, that's how much the temperature changes with increasing altitude in the atmosphere. So it's around 25 degrees Celsius on the ground. It's 20 degrees Celsius, 5 degrees cooler at a kilometer of elevation. And then at 2 kilometers above ground level, you can see that it's dropped another 5 degrees to 15 degrees Celsius. Every 1,000 meters of elevation, we change our temperature by 5 degrees Celsius. Great. But doesn't that imply that those warm temperatures near the ground are going to want to rise up through those overlying layers? Well, it's actually more complicated than that. So that's what the right side of the picture is showing. This is adiabatic cooling. Now you remember that's basically where the air parcel ends up changing its volume, and that volume increase results in a lowering of temperature. In the example over on the right, we've got this 25-degree parcel of air. It rises up to a kilometer of elevation, and you can see that it expands and it cools to 15 degrees Celsius. So 15 degrees Celsius is less than 20 degrees Celsius. So it's actually more dense than the surrounding air. If you were to shove that parcel of air up to 2 kilometers in elevation, the same thing would be true. All right, it would expand even further, it would cool even further. Now it's 5 degrees in its temperature, and that is 10 degrees cooler than the surrounding air, which is at 15 degrees. So the overall tendency, this arrow over on the far right, the overall tendency is for that air to want to sink back down towards the ground. So in other words, we would describe this air as being stable. Absolute stability is the condition that we get when our environmental lapse rate is greater than our adiabatic cooling rate. So there's a dry adiabatic cooling rate, which is where the air is unsaturated and you don't have clouds. And then there's a wet adiabatic cooling rate where the air is saturated and you do have clouds. But so long as those adiabatic rates are less than the environmental lapse rate, you have absolute stability. So the air here is going to have a tendency to stay down close to the ground. And the only way you're going to get it to rise is if you bring in some air mass that wedges it upwards. So for instance, you get a cold air mass moving in and you get some frontal wedging and you drive that warm air aloft. So that's absolute stability. On the other end of the spectrum is absolute instability. This is the situation that we get when our environmental lapse rate is less than our adiabatic cooling rate. So our adiabatic cooling rate is greater here, whether it's dry or wet, whether it's unsaturated or saturated. And as a result, basically, as that air lifts off the ground, the difference in its temperature relative to the surrounding air ends up getting greater and greater. So basically, this sort of feeds back on itself, and that mass of air is just going to want to keep lifting up further and further and further away from the ground. So that's unstable. Okay, now the more interesting situation is this one. This is what we get when we have conditional instability. We have a stable air mass when it's unsaturated. In other words, when it's cooling at the dry adiabatic rate. But the wet adiabatic rate is greater. Once it crosses that critical condensation level, then we're going to be using the wet adiabatic rate, and so that is going to be greater than the environmental lapse rate. That is unstable once you reach this situation where the air mass is saturated. So we start off over here on the lower left where we have the rising air being forced aloft, but you can see that it's cooler than the surrounding air, so its tendency is to sink. But once it gets above that condensation level, you can see that its temperature is greater than the surrounding air, and so its tendency is going to be to rise. So when you get frontal wedging, a cold air mass moving in, and when that rising air gets shoved up above that critical level, then basically it takes over and it keeps on rising due to its own ever-increasing buoyancy relative to the surrounding air. So that's stable at one point, but then it rapidly converts to being unstable once you get it above that critical elevation.
So we saw there the types of stability or instability that we can get there. And why does this matter? Well, the stability of the air, of course, determined by measuring the temperature of the atmosphere at various heights. And so we can see what happens. You know, if we continue to rise, we can have stability or instability or conditional instability. And why does this matter? Well, it determines what type of clouds will develop. If stable air is forced aloft, like we see in the stability, the clouds are widespread, they don't have much vertical thickness, and we don't really see any precipitation. But if clouds are associated with the lifting of unstable air, they keep getting larger and larger and larger, then we're going to get thunderclouds, we're going to get thunderstorm clouds, and possibly even tornadoes. So it's stability of those columns of air, those parcels of air, that really determine what type of clouds we're going to have and therefore determine our daily weather. So looking again at condensation, remember condensation is when water vapor in the air is going to be converted back to a liquid, either dew, fog, or clouds. And there has to be a surface in order for condensation to occur. So dew, is on grass and cars and porches and roofs and whatever. In the atmosphere, we have to have something else. We don't have those large surfaces, so we need something else. These are called condensation nuclei. And condensation nuclei can be things like dust, smoke, pollen, salt, if we're talking about being close to the ocean. And these are called hygroscopic or water-seeking nuclei because they actually really absorb water, so they can hold a lot of moisture. So when condensation takes place, these tiny little nuclei grow quickly at first, but as they continue to take the water vapor out of the air, their growth slows down. And so you end up with a cloud that consists of millions upon millions of these tiny little water droplets that are so fine they can remain suspended in air. If cloud formation occurs at below freezing temperatures, then ice crystals can form. So a cloud can have water droplets, it can have ice crystals, or it can have both, depending on the temperature where the cloud is found. So keep in mind, fog and clouds are essentially the same thing, just based on where they're located. So clouds are visible aggregates or visible collections of minute droplets of water or tiny crystals of ice. In 1803, we came up with this cloud classification scheme. It was done by Luke Howard, who was an English naturalist. And we've modified it a little bit, but his work provided the basis for our present day system. And we classify clouds based on form and height. And on pages 532 and 533 in your book, you have a drawing, and then you have these pictures. Okay, so you have this drawing, and then, the pictures aren't on here. Sorry about that. So what we're going to do is watch a smart figure video and go through all of the different types of clouds based on their form, what they look like, and their height.
Hello, this is Callan Bentley. Welcome back for another Smart Figure. In this video, we're going to take a look at the different types of clouds. And by the end of the video, you should be able to use two different characteristics of clouds, their shape and their height in the atmosphere, to assign a name to them. Okay, so here's the figure from your textbook that discusses cloud types. You'll notice that it's organized according to layers in the atmosphere. So we're going to discuss clouds that form at high levels in the atmosphere, over 6,000 meters or 6 kilometers, middle levels in the atmosphere between 2 and 6 kilometers, and then everything below 2,000 meters are considered low clouds. We're also going to look at the shape of the cloud. So we want to think about the cirrus shape, which is sort of a feathery or wispy appearance, sheets or layers called stratus, and then globular masses, which are called cumulus. Finally, we want to take a look at vertically developed cloud masses over here in the final column. So let's go ahead and take a look at these one by one. Let's begin in the upper left corner with high, wispy-shaped clouds. Those are called cirrus clouds. Generally, those are only going to be found up at really high levels in the atmosphere. Stratus is the shape. If we're still high in the atmosphere, we're going to call it cirrostratus. You notice that it's got some wispy aspects to it, and as the sun shines through it, it makes that sort of aura around the sun. Next up, moving over to the right, we've got cirrocumulus. Cirrocumulus are high globular clouds. We've got altostratus right here. Altostratus occur at middle altitudes, and you can see that they seem to have a layered appearance. And then at that same altitude, maybe you'll have the globular masses. That would be altocumulus. So alto is the prefix for both of those, and then their shape, stratus or cumulus. Down below, we've got nimbostratus. Those are rainy clouds that are down pretty close to the ground. Generally, they're a little bit higher up, though, than stratus clouds. So stratus clouds will be relatively thin, and they'll be closer to the ground. Stratocumulus are classic good weather clouds. You can see that they look puffy, like kind of cotton balls hanging out in the sky. Over here, if you've got larger masses, we might call them cumulus that aren't in layers. And then those cumulus can actually advance upward through the different layers of the atmosphere to make cumulonimbus clouds. And these are thunderheads. Oftentimes they have sort of an anvil shape at the top. You can see how it kind of overhangs up there at the top. That's typical of cumulonimbus clouds, and those are the real dangerous weather formers. Okay, let's quiz yourself now. Let's take a look at the images that we've got here. What sorts of clouds are we looking at? Let's take the left first. I'll give you a hint. These clouds are at medium levels in the atmosphere, and you can see that they're relatively sheet-like, so that would be altostratus. Okay, good. Over on the far right, you can see that towering sort of thunderhead kind of shape. So what is that? That's clearly going to be a cumulonimbus. That's probably the easiest one to spot. Over here on the left, what do we have? Pretty classic looking cumulus clouds there. They're not really in a sheet, so I wouldn't really call them stratocumulus. And then over on the right, let's take a look at that one. Sort of dark and relatively rainy looking clouds. So that's probably nimbostratus there. Okay, on the left, you can see feathery, wispy shapes, so that should instantly tell you that's got to be a cirrus cloud. On the right, looks pretty high up there, and you can see the little globular masses, so cirrocumulus. Good job. Final two here. Over on the left, you can see there's a high layer of little ice crystals through which the sun is shining, and it's making that classic-looking ring around the sun there. So this would be a nice example of cirrostratus. Finally, over on the far right, we've got sort of a medium altitude layer of puffy-looking clouds. These would be altocumulus. Okay, hopefully you got those. If you didn't, go back and take a look at the images again. There are photographs in your textbook that you can also use to review.
So there you saw the different types of clouds based on their appearance and how high they are in the atmosphere. So as a bonus question for watching this video, what would be the name of the clouds that are puffy at middle layers? You can send that to me in an email for bonus points. So fog, just clouds, okay? The difference, though, is that the base of the cloud is at or very near the ground. So fog is made up of the same condensation nuclei and water vapor that clouds are. Their appearances, their structures, they're exactly the same. The difference is just their location and how they form, the method of formation. So we're going to watch another smart figure video here and look at the types of fog.
Hello, this is Callan Bentley. Welcome back for another smart figure video. This time we're going to take a look at fog. And after watching the video, you should be able to describe how the 5 principal types of fog form. So fog, if we need to define it here, and we probably do, is basically a cloud that's sitting on the ground. So there's really nothing fundamentally different between what we see in the sky as a cloud and what we drive through very cautiously, like in this picture, and consider fog. It's basically just suspended water droplets in the air. So there are several different kinds of fog we need to consider. The first is a radiation fog. This is a kind of fog shown here in California's San Joaquin Valley that forms on cool, clear, calm nights. And this is basically when the ground is radiating away heat pretty quickly. And as a result, the ground cools off a whole lot. And then that actually can cause the air that's very close to the ground to be cooled below its dew point. The water will condense out of the air and it'll form a fog. Another example of a fog is an advection fog. This is what you get when you have warm, moist air moving over a cool surface. So here at the Golden Gate in San Francisco, the ocean is quite cold, and so the air is warmer than the ocean. As it moves over it, it triggers cooling of that warm, moist air below the dew point, so condensation makes a fog. This is advection fog. Another example of a fog is an upslope fog. This is what happens when you have air that's basically being forced up and over some sort of topographic obstacle. If it goes high enough, it will expand and cool adiabatically, and that can lower it below its dew point. So once again, condensation will form a fog in that circumstance. Upslope fog. This is an example of a local phenomenon called a steam fog. What's going on here is that you have relatively warm water and the air is the cooler one. So this is kind of like the opposite of advection fog. What's happening here is that the warm water is giving off lots of water vapor. It's hitting that cool air and basically recondensing immediately. Lastly, we have to consider the frontal fog, also called the precipitation fog. This is what happens when you have frontal wedging, so a warm air mass meeting a cool air mass. The warm air mass is shoved up, that triggers rain, and that rain falls down through the cooler air mass. Near the dew point, enough rain will evaporate to produce fog. This result is a more or less continuous zone of condensed water droplets reaching from the ground up through the clouds. Here's a map showing the average number of foggy days per year in different portions of the United States and Canada. You'll notice that there are heavy fogs, in particular along the coastal regions, so the Pacific coast, and then also in New England. There are cold currents in both of those places. We end up seeing advection and radiation fog along the Gulf Coast, and then upslope fog is particularly common, basically where the Great Plains meet the Rockies. Okay, let's test ourselves here. This is coastal Maine. We've got cold water here, and now you need to identify what kind of fog this is. Well, it's probably going to be an advection fog because Maine is right there adjacent to one of those nice cold currents. So those cold currents basically can interact with warm air above them and trigger advection fogs.
So now that we've seen how clouds form, we're going to finish out the chapter looking at how precipitation forms. So we know that all clouds contain water, right? That's how they form, from the condensation of water vapor. Why do some form rain and others don't? Well, there are two types of processes, or two different processes, that kind of explain what happens with precipitation. So we have the Bergeron process and then the collision coalescence process. So we're going to look first at the Bergeron process. Okay, and this figure is from page 538 in your book. So the Bergeron process is what's going to generate a lot of the precipitation that occurs in the middle and high latitudes. This happens within cold clouds. So this is going to be our Bergeron process occurring in cold clouds. So let's take a look at what happens. Well, cloud droplets can remain liquid at temperatures as low as -40 degrees Celsius. This is called supercooling. If water can remain water, so if liquid water can remain liquid water at temperatures below freezing, it's called supercooled, and it becomes a solid when it impacts a surface. And so this kind of explains what happens to airplanes as they fly through clouds that have sub-zero temperatures. When that water that's been supercooled hits the body or the wings of the plane, it causes icing on the plane. Supercooled water droplets also freeze upon contact with these ice nuclei, or what we call freezing nuclei. So these ice nuclei are pretty sparse, and so cold clouds consist of supercooled droplets of water intermixed with a lesser amount of ice crystals. So here's kind of what we've got at first. Okay, so here's our water vapor molecules. Again, this is very cold, but they're supercooled. Okay, so they're going to remain in liquid form. All right. When ice crystals, we've got a little ice crystal here, and those supercooled water droplets coexist, this is setting up a perfect process for precipitation. Ice crystals have a greater affinity for these liquid water or for the water vapor rather than liquid water. And so they're going to collect this water vapor at a faster rate. So you've got this ice crystal that starts out here, this size, and then becomes what we refer to as snow, because these little water vapor molecules are going to be attracted to this ice crystal, and so it's going to start kind of collecting them and growing larger and larger. The water droplets, okay, so what we're seeing here as cloud droplets, evaporate in order to maintain saturation. And so this provides continual moisture for this growing ice crystal. Eventually, they grow large enough that they start to fall in the form of snowflakes. When the Earth's surface is about 4 degrees Celsius, which is about 39 degrees Fahrenheit or higher, snowflakes will melt before they hit the ground and fall as rain, which we know that this is something, we're all familiar with this in Southwest Arkansas. It's snowing all around us, but it gets here and it falls as rain. Well, what's happening is that the clouds are forming snow, but as it goes through the warmer temperatures, as it's falling from the clouds to the ground, it melts and falls back as rain. So this is the Bergeron process, happens in cold clouds, responsible for snow formation. The other type of precipitation is the collision coalescence process, and this occurs in warm clouds, and this is shown for you on page 539. So what happens is if we have a cloud that's composed of only liquid water droplets, some of them have to be larger than 20 micrometers, which is 0.02 millimeters, in order for precipitation to form. And so that's what you're seeing in this top figure. Most cloud droplets are about 0.02 millimeters, but then we have to get some larger ones in here. Large cloud droplets are going to fall faster than smaller droplets. So as they fall, they're sweeping up the smaller ones into their path and continue to grow larger and larger. And so as they increase in size, their velocity increases, which means they pick up more droplets, but they start to become flat. Okay. As it approaches about 4 millimeters in size, it develops this little depression, and as it continues to grow larger, about 5 millimeters, the depression continues to grow and it splits into several more raindrops. And then those grow, and the process essentially just keeps going over and over and over again. Raindrops can only grow to a maximum size of about 5 millimeters. And at that point, they're falling at a rate of 20 miles per hour. Beyond that size and speed, the water surface tension, which is holding all these drops together, just can't compete. It can't withstand the drag, and that's what allows them to fall apart. Okay, so this is the collision coalescence process that occurs in warm clouds. So what are these different types of precipitation that we can get? We've discussed kind of snow and rain, but then we have all sorts of other names for these different types of precipitation. So if we look on page 541, we have figure 17.29, which is looking at winter precipitation. Okay, so here's our cloud. Okay, and so we've got cold air, we've got the Bergeron process that's occurring here. Okay, and here's our 0-degree line. Notice we're forming snow in all circumstances up here in this area that's less than 0 degrees Celsius. But if the snow encounters warm air, it melts to form raindrops. Okay. If it melts as it goes through the upper atmosphere, but it encounters this layer of cold air close to the ground, it becomes super cooled again, and when it hits a substance, it freezes. This is called freezing rain. This is bad. Okay, freezing rain is bad. This is when we get ice storms. Okay, and that's something we're all familiar with around here. So it falls as rain, but it becomes super cooled because of the cold air at the surface, and as soon as it touches something, a car, a power line, a tree limb, it starts to freeze. And so we get layers upon layers upon layers of these frozen raindrops, and eventually we get the downed power lines and the downed trees because they can't withstand the weight of all of that ice on them anymore. Now sleet, okay, is when we have a deeper freezing layer. So instead of super cooling, we actually get the rain becoming completely frozen before it hits the ground, and that's called sleet. Okay. Now, if the snow doesn't encounter any warm air at all on its way down, then it starts as snow and it continues falling as snow. Okay. Now on page 540, there is a table that you should be familiar with on the different forms of precipitation. Of course, rain, 0.5 to 5 millimeters. Drizzle is about 10% of that size, and then mist even 10% more of that. Now we've gone over sleet, freezing rain. Rime is ice, basically little ice feathers that point into the wind. They form as a supercooled cloud or a fog. This is, there's a picture of this somewhere in your book, but I don't see it now. Oh, there it is, page 542. There's a picture of rime. Basically, this is like frozen dew. And you'll see this as we start to have frosts. You'll see some of this sometimes set up like rime. And then we have, of course, hail. Hail is 5 millimeters to 10 centimeters or larger. Hail is produced in the cumulonimbus clouds, where you've got frozen ice particles and supercooled water that's going to exist. So here is an explanation of the formation of hailstones. This is on page 542 in your book. So in these cumulonimbus clouds, you've got updrafts of warm air, you've got downdrafts of cold air. And so what happens is one of those ice nuclei, or these cloud nuclei, they kind of get caught in this cycle, okay? And they can even continue going around and around. And they'll fall if they kind of stay in this little middle zone here that's right between the cold downdraft and the strong warm updraft. And so you see this picture of a hailstone here. This was a cut hailstone. It fell in 1970 in Kansas. It weighed almost 2 pounds. And you see kind of this clear layering and then kind of this milky looking ice there. And so you kind of have this layering effect. And this is due to wet growth and dry growth. The wet growth, which forms the clear ice, occurs when hail collects those supercooled droplets fairly quickly, and the surface of the hailstone then remains wet. Dry growth is when the droplets accumulate at a slower rate, and so it traps air bubbles in there, and that's what gives it that milky appearance. The largest hailstone ever in the United States was in 2010 in Vivian, South Dakota. It was 8 inches in diameter and weighed almost 2 pounds. It was bigger than this one here that we see. So how do we measure precipitation? Well, rain is the easiest form to measure, and we have some different types of rain gauges. We have the simple rain gauge that we can just set out a cup that's got an inch in diameter, or we can have this standard rain gauge that has a funnel that collects in 1 inch of rain, and then the measuring tube basically allows us to get this ratio that sets up to determine how much rain we get. And then we have a tipping bucket gauge that is hooked up to a recorder. But most of the time what you'll see is something along these lines of this standard rain gauge. Snowfall typically measured by depth or its water equivalent, how much water is in the snow, and that varies. And then we have radar, and radar is used by the National Weather Service to produce, these maps that we're all familiar with. These radar units send out radio waves, and they penetrate clouds that are composed of small droplets, but then they're reflected by either hail or ice crystals or larger raindrops. And so that's called the echo, and that's what's received back and displayed here. The echo is brighter when the precipitation is more intense. And so that's when we get, the yellow and the orange and the red colors. And so these, of course, are useful in short-term forecasting. So that brings us to the end of chapter 17, moisture, clouds, and precipitation.